Okay, so what we're going to be doing is deriving the kinematic equations. It's these four here that any person who's ever taken a physics class is familiar with. So it was always hard for me to figure out where the hell these were coming from. So we're going to derive them. So the first thing that we're going to do is start off with Newton's second law, which is force is equal to mass times acceleration. Mind-blowing, right? Okay. So the first thing you're going to want to do is rearrange this so that acceleration is force over mass. We know that acceleration is the time derivative of velocity, so we're going to replace a with dv dt. That gives dv dt is equal to force over mass. Then we're going to move dt over and integrate from initial to final and from 0 to t. And we just integrate, so that's going to give us vt minus v naught is equal to f over mt. I'm going to skip a lot of the basic calculus steps because if you can't figure out what steps I'm skipping, then it's going to be more beneficial for you to actually go back and review calculus than to try to figure it out this way. Trust me, I learned that the hard way. If there are any calculus skills that you are skipping out on, use substitutions, integration by parts. Do it again, and do it 80 times until you learn it. So then we're going to rearrange, and we get velocity as a function of time is equal to initial velocity plus f over m t, but f over m is equal to acceleration, so we're just going to replace that. Acceleration times time, and this gives us our first kinematic equation. So then the next thing we're going to do is we know that velocity is the time derivative of position. So we're going to replace this v with dx dt. So then we get dx dt is equal to v naught plus at. I'm also going to skip out on some of the vector signs that should be intuitive. That acceleration needs a vector, and this needs a vector. V naught does not need a vector. Maybe it does. See, now I'm questioning myself. V naught does need a vector. Okay, great. So then we're going to move dt over, and we're going to integrate from x naught to x as a function of time. And again, from 0 to t, v naught plus at dt. It's like tau, that's a t. And that's going to give us x of t minus x naught is equal to v naught t plus 1/2 at squared. And then we just move it around, and we get x of t is equal to x naught plus v naught t plus 1/2 at squared. And that is a crappy box. Let's try that again, you guys. We can't try that again. Pretend that's a really good box. No, that's gonna bother me. x of t equals x naught plus v naught t plus 1/2 a t squared. We're going to do a really great box now. And that's our second. Alright, so those were always the easiest two to derive. The last two is where I would get confused. So we're half doing this for you, half doing this to make sure I can pass basic questions on a qualifying exam. So to get equation 3, we're going to need to, let me just draw some lines here. We're going to need to rearrange equation 1 so that it is v final minus v initial. No, let's do not. Initial is equal to a t. So we're going to take equation 2, x is a function of time, is equal to x naught plus v naught t plus 1/2 a t squared, and we're going to replace this in there, and that gives us x of t is equal to x naught plus v naught t plus 1/2 v final minus v naught t, and then we notice we got a negative 1/2 v naught t and a positive v naught t, so we're going to simplify that, and we get x of t is equal to x naught plus 1/2 v final plus v naught t, and this is our third kinematic equation. And the last one we have to derive is velocity as a function of position. So we know we're going to need our x's, so we're just going to go ahead and take equation 3 here and rearrange it so that we have x final minus x initial is equal to 1/2 velocity final plus velocity initial t. And what are we going to do next? We need to actually solve this as time as a function of position. So solving for t as a function of position, we're going to get to x final minus x initial over velocity final plus velocity initial, and we're going to plug this into equation 1 for t. So velocity as a function of time is equal to v naught plus a t. We're going to go ahead and move v naught over, so that's going to really just change this over to v final minus v initial is equal to a t. We're going to go ahead and plug in our t as a function of time into this equation here, giving us v final minus v initial is equal to acceleration to, oh, where'd it go? Things just disappearing, but that won't. Okay, let's go with it. Acceleration, now it does. Computers, right? Alright, acceleration times 2x final minus x initial divided by velocity final plus velocity initial. We're going to need to get this velocity over to the other side, which is going to leave us with v final minus v initial times v final plus v initial is equal to 2a x final minus x initial. Distributing this out, we get v final squared. That cancels out, that cancels out. Minus v initial squared equals 2a x final minus x initial. And to make it match, we're going to move it over. So that means v as a function of position squared is equal to v naught squared plus 2a x final minus x initial, and that is our fourth kinematic equation. Okay, so what's the difference between all these? Like, really, what's the point? This is velocity as a function of time, whereas this is velocity as a function of position. That is it. I hope you found that helpful. If you didn't, that's okay. Maybe somebody else can explain it better than I did.